All right. So this is material from class 7 from geometric methods in algorithm design taught by Professor Khot at NYU. And class 7 means today's material is balanced graph partitioning. Balanced graph partitioning. And more the main discussion, sparsest cut. Sparsest cut. So we'll start with balanced graph partitioning. We'll go to sparsest cut, the problem, we'll define how it works. And then we'll look at an approximation algorithm to that, and it will lead us to a very nice mathematical formulation of, metrics and embedding in metrics and stuff like that. So let's start with the balanced graph partitioning first. So what is balanced graph partitioning? Balanced graph partitioning, just from the problem description, is, let's say you are given a graph G with a vertex set and an edge set, right? What the problem description is, find, let's say, a 1/3, 2/3 partitioning of this graph. If this is the graph, find something which is, relatively balanced, cuts it into S and S bar, such that the number of edges which are crossing S and S bar are minimized. So find a 1/3, 2/3 cut SS bar that minimizes the number of edges going between S and S bar. This is a very, what does it mean to minimize the number of edges given? Like, this is a very vague description of the problem. And, that's okay. That's all I'm saying. That's okay. This is a very vague description of the problem, and this is anyway not going to be the majority of the discussion today. The majority of the discussion will be sparsest cut. But we'll start with this because sparsest cut, an algorithm for sparsest cut actually leads us to an algorithm for, let's say, balanced graph partitioning. So the requirements that the algorithm places, that S, or let's say S bar, has to be greater than or equal to n/3, right? And what this balanced graph partitioning is in reality is just a clustering problem. If you think about it, what you want to do is split the graph into relatively same sized chunks such that the number of edges between them are as few as possible, which means that there would be a large number of edges running between them. However, that is not our concern. The concern is that number of edges between them has to be minimized. So it's really a clustering type of problem if you think about it. So what is sparsest cut? I've been hyping up sparsest cut for the last couple minutes. What is that? What does that mean? Well, from the description, from like the words, sparsest cut, what does it mean? It means it's the same essentially as balanced graph partitioning, but now we do not enforce the balanced condition. So what the sparsest cut means is something which absolutely cuts the graph into the fewest, let's say, the most sparse version of itself. So what does that mean? Let's define sparsity. I think this definition will look familiar. So if the number of elements is, let's say, less than half, we need to enforce that. The sparsity is the minimum over all such sets such that the cardinality of that set amongst that graph is less than half of the graph. So that's the minimum of the number of edges crossing between S and S bar divided by the number of elements in S, right? So if my graph was D regular, this is exactly the same as how we defined h of g, except just the constant 1/d. We defined h of g as the minimum over edges S bar divided by d times the number of in S, right? So this is essentially the same as the Cheeger's number hg, except that this is instead of a d-regular graph, it holds for any graph. So for a d-regular graph, let's say, because we had an entire class on d-regular graphs and eigenvalues and so forth, we had that h of g is less than 2 lambda and is greater than lambda by 2, right? Where lambda was the eigenvalue gap. Essentially, let me remind you, this was the second highest eigenvalue of the Laplacian operator for the graph, right? So what we have is, and we also, from the algorithm, the way we discussed it, what we do is calculate, let's say, the eigenvector v, zero out the negative numbers and only carry the positive numbers sorted from descending to ascending, right? That's how we formulated that graph. We find a set S which minimizes this quantity over, let's say the level sets of this particular vector. So what we have is that this lambda, we know that the h of S is less than this lambda here. So what we have actually is h of g is obviously going to be less than h of S, because h of g was the minimizer over the entire graph, and h of S star, let's say S star was a graph returned to us by that algorithm. H of star is a particular set. So h of g will always be less than h of S star, and h of S star is less than lambda. We did this at the end of the last lecture. You can refer to it. So what I conclude is that because h of S is h of S is it's less than root 2 lambda, basically. That's this side of the inequality. So h of S is less than root 2 lambda, and lambda is less than 2hg. So this entire thing is less than 2 times root of hg, right? All I'm doing is putting lambda as 2hg here. So essentially what I'm trying to say with this quantity here is what we have here by the end of this number is that we can find a h of S star, which is obviously going to be greater than h of g, but it's going to be less than square root of h of g, right? And h of g is going to be a small quantity, so square root of h of g is going to be a large number. So the thing is that this number could be large, like very large. What we desire in terms of an approximation algorithm, to have a S star which is some function of n and h multiplied with h of g. We do not like this function on h of g, like the square root, right? We would like to be something of a multiplicative kind of function, and then we could say that this is an f of n approximation to the algorithm. Again, all of this is just for the d-regular graph, because h of g was h of S from last lecture was only for the d-regular graph, but it gives some intuition. Like we would want to find some sort of an approximation of this form, not of this form, right? That's the main idea. There's the main desire for today's, and we would call it an f of n approximation. So the theorem is that indeed we can find an f of n approximation, and this f of n would be log n. We'll see how, of course, we'll see how. So the theorem is that phi of g, now I'm talking in the most general case, which, let me remind you, is edges S bar divided by the number of elements in S, and S is the smaller of the two sets, right? This can be approximated with a factor of f of n, where f of n is log n. That's the theorem. So we'll prove this theorem. So first, let's go back and forth. Let's confuse the viewers as much as we can, and we will now comment how we can use the sparsity argument to find a balanced graph partitioning. If I'm able to convince you that if I'm given an algorithm to find me the sparsest cut, I can find a balanced graph partitioning. And then if you're convinced, we can forget our discussion about balanced graph partitioning and just look at sparsity. So let's say given that our graph G has a 1/3, 2/3 partitioning, which cuts an alpha portion of the edges, where alpha is like a small number, whatever, a small number. So how would an approximation to this algorithm look like? If you look at it closely, the reason I was so, a little bit lost when defining this particular problem definition is because there are two instances where you can, two levels to this problem. Basically what I'm saying is, let's say I have an algorithm, let's say I have an approximation algorithm. What it can give me is an approximation to either the balance or the approximation to the portion of edges you cut. Like there are essentially two levels to which you can approximate. So we can, let's say if we can find a 1/10, 9/10 approximation which only cuts, let's say, some alpha fn order edges, we will call it a pseudo approximation, because we don't really know how to define approximation for this problem, because there are two constraints or two, let's say, deliverables that this algorithm has, like two deliverables that this algorithm must give to the user. So let's say that we call it a pseudo approximation, essentially. So we don't really give a 2/3, 1/3 partitioning, but let's say a 1/10, 9/10 partitioning, and which also has an alpha f of n approximation to the number of edges that it actually cuts. So how would you, as the viewer, go about designing such an algorithm? If I gave you an algorithm for the sparsest cut, let's say you have that, how would you convert that into a balanced graph partitioning? Well, the idea would be very intuitive if you think about it. Let's say this was the actual theoretical, unknown to us, some oracle only knows. S bar 1/3, 2/3 partitioning, which is the actual real balanced partition of this graph, right? So when I run my sparsest cut algorithm, because it's going to give me some sparsest cut, if that set is very small, let's say I run this sparsest cut algorithm, let's call it SC, on this entire graph, and it returns to me some small T1, some small set T1. And because it's a sparsest cut algorithm with some Fn approximation, we can be sure that the number of edges going out of this, or let's say the number of edges relative to the size, is small. So the sparsity that this specific very small cut has, the sparsity is small. We can be, assured of that from the sparsest cut algorithm guarantee. But we cannot be assured of the size of T1. So what would you do? What would you do is, well, take T1 out and run again. So you run G on G on a sparsest cut. You take T1 out and you run it again. Let's say it gives you some T2. What you want to do is take T2 out and run it again and again and again until T1 union T2 union Tn is, let's say, 1/10, which was your requirement. 1/10, it could be, you could place 1/8 for all you care, right? So the idea is that what I'm trying to convince you is, I'm not going to be able to prove this because I don't understand it myself, but what I'm trying to prove to you is, if I take out smaller chunks of the graph, which are also sparse in themselves, they cannot affect the sparsity of the entire graph on a whole. Because what happens is, once you take T1 out and you run the sparsest cut on G devoid of T1, the sparsest cut will return an Fn approximation of the current graph's sparsity of the phi of G devoid T1, The sparsest cut will give me an Fn approximation of whatever's left now. Now what I'm saying is that the sparsity of whatever is left now is not too different from the sparsity of whatever was there to begin with. That's the main condition, that's the main argument here. And I don't know how it is proved in the notes, and I don't understand it myself, but it makes sense to think about it in the sense that if I take out small numbers, if I take out small sets out of the graph, how could I impact the sparsity much, when then they themselves are small and the number of edges relative to them are small again, because it's again a sparsest cut algorithm. It kind of makes sense that you do not impact the original sparsity of the graph as much as you think. So if you are able to just accept that for the on the face value, I can move on, and I can show you some really good, like really interesting things, which would be about the sparsest cut. Now we could deal about this. Now we could like focus on the sparsest cut. So bottom line is, and a sparsest cut algorithm can be leveraged to give a balanced graph partitioning. Okay, let's accept that for a moment. Let's accept that for now and move on. So now the focus though, now the focus of the entire talk now, the focus will be on phi of g, which is the, edges S bar divided by number of edges, number of elements in S. Well, this as a notion of sparsity is a little bit, not too nice, because it's not as nice as this notion. Let me just say it. Phi tilde is the number of edges that run between S and S bar divided by S and S bar. So now by doing this notion, what we can do is actually remove the constraint that S has to be less than n over 2, because now this thing is symmetric. Like this thing is symmetric. Of course, the minimum. S and S bar both appear in the denominator, so this thing is symmetric. Now what the claim is that phi tilde of g is up to let's say a factor of 2 of phi of g. Like these two, the idea is that these two quantities, phi of g and phi tilde of g, are coupled. They are not too independent of each other. They are related to each other. So we can focus on phi tilde of g, which is actually a better, let's say, it will lead to a better analysis. It will lead to a better, more intuitive definition, because this thing is symmetric compared to both the sets on either side. So this thing, the bottom line of this slide, I want you to understand is that phi of g, however this is defined, is just an arbitrary definition, right? Some mathematician defined it in such a manner. And this phi tilde g, which is again another definition which some mathematician defined, these two things are related to each other. These two things are coupled. They are not they're not going to run away from each other. If I have a handle on this, I can have a handle on this, basically. So what's the benefit of defining it in such a manner? Like, what did I gain? So now I have an idea of a cut metric. Oh, let's say no, I'm going ahead of myself. Let's say I have a cut S and S bar, and I defined a distance function, which is essentially a metric. Essentially, I wanted to keep the discussion simple. I want to define a distance function between 2 points I and j of this graph. Now, given a cut, how would I define it? Let's say I define it as such. 1, if they are on the opposite sides, if I lies here, j lies here. 0, if they are on the same side. If same side. This is how I define a distance function for a particular cut. So this distance function is a very specific, like this distance function only holds for this particular cut. That's the main thing to notice. If they are on the opposite sides, the distance will be 1. If they are on the same side, the distance will be 0. That's how we define our distance function. Now what this is called is a cut metric. Cut metric of S, let's say, of S bar. Now why is it called a cut metric? Like whenever there is a metric, now the mathematicians are excited. Like why? Why did you call it a metric? Does it satisfy metric properties? Let's verify. ds I comma I is 0. Is it? Well, if it's on the same side, we define it to be 0, and I are on the same side always. So dsii is 0. dsij is equal to dsji. Is it? If I and j are on the opposite sides, it doesn't matter if you query the metric as dsji or ij, the distance is 1. And if they are on the same side, then this is 0. So it's also like this also is satisfied. Does it satisfy the triangle inequality? Let's see this. This is basically the main one. The above two were just to warm up. If so, the triangle inequality is that Dik is less than Dij plus Djk. All of them are obviously subscripted by S. So is it true? Let's say if Dsik, if I and k are on the same side, let's see the two cases, right? This could be 0 or this could be 1. If I and k are on the same side, that means it is 0. And it is less than Dsij, it's always either 0 or 1. Or Dsjk, which is always either 0 or 1. If they are both 0, that means Ij are on the same side and Jk are on the same side. That means Ik are also on the same side. So 0 is always less than or equal to 0. If Ij are on the separate other side and Ij are on the same side, that means Jk must be on the separate side. So this will always be less than 2 because Ij contribute to a distance of 1 and Jk contribute to a distance of 1. So this case is trivial. If Ik is 1, that means I and k are on the opposite side. So I is here, j is here. Oh, sorry, k is here. There can only be two possible choices for j. Either j lies here or j lies here. J lies here. So in this case, case 1, Dsij is 0, but Dsjk is 1. So 1 is satisfied. If is on this side, on this case, d of ij is 1, but jk is 0. So again, 1 is less than or equal to 1. So triangle inequality is also satisfied basically. So this is a metric. This is a genuine metric. The cut metric. It's a legitimate metric. Why did we do this? You'll see this now. What will this quantity be if we try to express it in terms of the cut metric? Well, this is the number of edges crossing the cut, right? Edges crossing the cut. So the number of edges which are crossing the cut, in terms of the cut metric, the number of edges which are not crossing the cut have a distance of 0. The number of edges which are crossing the cut have a distance of 1. So if I sum up all the edges of the graph in this particular cut metric, do I get this? For the edges which are on the same side, they contribute 0. For the edges which are on the opposite side, they contribute 1. So the number of edges which are crossing this particular S bar is essentially the sum of the cut metric over all the edges. Okay. How about this quantity then? If I had to express it in this particular fashion, let me write it as some sum over ij. But a sum over what? A sum over what? If I take a sum over all pairs, let's say, all pairs I, j in the VXV, like vertices as vertices, is this equal to this? Let's try to reason about it. If I and j, the only way this sum is ever 1 is when I and j are on the opposite sides, right? Now, how many times when I sum it over all possible pairs is I and j on the opposite side? Well, in a total sum of all possible pairs, if I select one pair here, if I select one vertex here, I, and I'm summing over all possible pairs, all the possible vertices which are amongst the S, they contribute 0. All the possible vertices which are on the other side contribute 1. So this, for this particular, just for one vertex on the left hand side, we get a contribution of S bar. Now how many vertices are there on the S side? Well, there are S of them. So this is exactly equal to SS bar. So now the sparsity for a given set can be written as the sum over edges of the cut metric ij and the sum over vertices, well, all pairs of the cut metric ij. It's a very nice formulation, right? Now I have a set cut S. I can take the sum over all edges, let it be the numerator, and the sum of all pairs, let it be the denominator. This is precisely the The new definition, see, I caught my mistake. It has to be phi tilde. The new definition of the cut, the sparsity that we defined, right? So yeah, that's a very nice, that's a very nice that's good progress actually so far. We defined a cut metric and we defined the sparsity in terms of the cut metric. So yeah, let's also, you know, analyze this metricness of this particular thing a little bit more. So let's define something first. I define the endpoint metric. Endpoint metric is just a set X, which is of cardinality n, and a function D, which is of the form which takes elements from set X and another element from set X and maps it to a real value, right? And it's a symmetric function that Dij is equal to Dji. Like, I'm just defining the metric like in terms of mathematical formality. Dij is equal to Dji. Dii is 0. Dii is 0, and it satisfies the triangle inequality. That is Dik will always be less than Dij plus Djk, right? Again, this is again two, like, function of two variables. So I'm just, you know, it's going to be a little bit cumbersome to write it in proper formality. But here, this is like the mathematical definition of a metric. I'm sorry. A metric is nothing but a collection of points and a function on those points. A function which takes two of those points as input and returns a real number as an output. Now for let's say this is just for an endpoint metric, right? But this definition could be easily extended to continuous spaces. So for let's say if my X was, let's say, real numbers, so the metric could be just, you know, metric could be defined in whatever way it is. As long as it satisfies these three things, it's a metric. So like the common metric is distance between A and B is B minus A, the modulus of it, right? This is how we define the, let's say, on real numbers. Like, this is a metric. Like, this is a very common, like, very straightforward metric. It satisfies the triangle inequalities and everything. Same also works for, let's say, Euclidean norm. Like, that's a metric. So another thing to note is, like, this is just a very nice definition of a metric. Like, this is mathematical formality here, and I enjoy mathematical formality a lot. So another thing is now to note is, if I have a metric D and a metric D prime, then any positive combination of them is also a metric. Okay, let's verify it. Dii is 0. Dii is 0. D prime ii is 0. So in a positive combination, it will also be 0. Dij, ji are symmetric. So the positive combination will also be symmetric. The only thing we need to verify really is the triangle inequality. So let's say a metric satisfies the triangle inequality. So C is less than A plus B, right? And C can be I just want to make the notation smaller. So C is Dik and A is Dij and B is Djk, right? Essentially. So C is less than A plus B, that's in metric D. C prime is less than A prime plus B prime, that's in metric D prime. So mu C plus mu prime C prime is less than mu A plus mu B plus mu prime A prime plus mu prime B prime, right? And let me call, so yeah, I mean, so this basically so let me call this as the new metric, and let me call, So basically what I'm saying is D of A, like point I and B, is the mu times D plus mu times D prime, D double prime. Basically what I'm saying is that it also satisfies the triangle inequality. So any non-negative or positive linear combination of metrics is also a metric. Positive linear combination of a metric is also a metric. So this is pretty interesting for the following reason. The reason being that I will define a class C which has all positive combination over all possible sets of a graph. This is a class. This contains every possible metric you can define on my graph. Take every possible cut. There are 2 to the 2 to the n of those, and take every possible linear combination of that cut. This is the big class C. Like this is the cut class, also obviously defined on n points and some particular graph which goes in to induce these cuts, whatever. Like this is the class. This is like as big as it gets. Like I can take all possible cuts, a linear combination of them, obviously given mu is positive, obviously. Like that's like that's what makes metric properties hold. This is like the big class, right? Now we can also define a class L, let's say, which has all, let's say for points 1 to n, the class L has all possible L1 metrics. So what this L1 metric mean is that it takes from points, like points in the graph, it maps a vector to them, x1, x2, x3 up to xn, all of which have dimension, let's say m. So all possible such metrics, such that we define the distance function as the L1 norm of L1 distance between 2 points, right? Like all possible n point, m dimension L metrics. M could also be a M could be variable too, like it doesn't have to be fixed. It is every possible L1 metric, The only thing is that it has to be measured in L1, like that's it. That's the only constraint there is, that this has to be measured in L1. So the distance is, this is obviously, let me write it clearly, x superscript I subscript j minus x subscript k and modulus and sum over all k. Basically the sum over all coordinates of the individual differences of the coordinates. This is every possible L1 metric you can think of. That's a class. So I have got two big classes, right? One is every possible cut metric, and the other is every possible L1 metric. Now what I will prove is that C is equal to this L class. So every possible cut metric is an L1 metric. We will prove that. So to prove that, we need three particular, we need to go about it in 3 ways. Number 1 is that both classes are closed under positive combination, non-negative. It's just I just wanna make it easy to write. Number 2, C is a subset of L. Number 3, L is a subset of C. All right. This is a very critical thing to prove. Both classes are closed under positive combination. Why is that critical to prove? That is, if I can find the, if I can take C and reduce it into a very small set, and I can map them to L 1-to-1 in L1. If I take a non-negative combination of every one of those C's in such a fashion, I will be sure to lie in C, and therefore I will be sure to lie in L, because a linear combination of C translates to a linear combination of L. We'll see. Haha, get it? Will L. So, to prove that, well, C is closed under linear combination, closed under non-negative combination. Well, I don't think I need to prove this, because that's how we defined C. C is defined as every possible non-negative combination of cut matrix S. If there was one which I could reach by doing a non-negative combination of pre-existing cut matrix, I would have been in C, because that's how I define it. Like, that's how I define it. Every possible non-negative combination. It's a big class. Like, it's a big class of all real numbers, of all everything. Like, this is a big class. Like, this is, you cannot, it's not something that you can think in finite terms. Like, this is a class which has all non-negative combinations. So that's okay. Duh. How about L then? How about L? Let's say I have a metric D. I have a metric D1 such that it takes xi and xj and it maps it to vectors vi and vj. Right? This is number one. I have a D2 which has xi and xj and it maps it into ui like uj. Right? This is two different metrics. These are two different L1 metrics. Now I want to prove to you that a linear combination mu1 d1 plus mu2 d2 is also a metric such that d3 xi xj maps to some other vector, let's say wi minus wj. This is what we have to prove, that a linear combination of these two vectors, these two metrics, translates to another metric which is also an L1 metric. That is, it maps to a W which also has which is also measured in L1 norm, right? So how would one do that? Let's think about it. It's not trivial. But once you see it, it's beautiful. So let's say my D1 space was something like, take my point X and map it to a vector V. My D2 space was take a point X and map it to a vector U, such that when I have two different vector V is like this, vector U is like this. When I have two different X and Y, there is another V1 and another V2. So that when I take the difference of these two things, I can take the difference element wise, modulus them and sum them. Now I want to make it to translate. I want to translate it to another one which goes to, let's say, W1 and W2, which preserves the fact that if I add these two with a linear combination, I add the sum of these two with a linear combination. Well, here's the kicker. How about I just stack them? Wait a second. 15, 16, 17. So how about I define W as just V stacked on top of U, I guess. I never mentioned any restriction on the number of dimensions, now did I? This is a very clever trick. You can do this basically. Just stack these two together with the appropriate coefficients, mu1, mu2. So whatever the sum here, whatever the mu1 d1 plus mu2 d2 translates to precisely D3 in this stacked regime. If you think about it for a second. All you do is just stack these two, the x's. This D was a space which takes my x set to an Rm, right? Like this was the L1 space, right? I just stacked these two on top of each other given a weight view or mu, such that when I calculate the distance in this new metric, all I'm doing is taking the distance here and taking the distance here and adding them up with a particular weight function, weighted whatever. So this stacking regime exactly makes them equal. So like this is pretty crazy if you think about it. Like this is pretty crazy. Like all you did was take two L1 spaces and stack them together, and you have any linear combination, like any linear combination you can think of, just keep stacking them, just stack them. This will preserve L1 distances altogether. Again, it had the dimension could be as high as you want, like it could be infinity, it could be arbitrarily high. So now, number 2, prove that the C is a subset of L. It's pretty simple if you think about it for 1 minute. If I have a cut S and S bar, this is just one particular element of my entire class, right? A non-negative combination of all of them also includes this itself, like 1 time this plus 0 times everything else. So what is the DS? D of S is 0 when they're on the same side, and D of S is 1 when they're on the other side. How would I translate to an L1 metric? Here's how. I take every point in S and map it to 0. I take every point in S bar and map it to 1. Now in this particular regime, xi minus xj, it's only a one-dimensional, so it's only a one dimension. So this is essentially just saying xi minus xj absolute value. This is equals to 1 when they're on the opposite side, and this is equals to 0 when they're on the same side, either 0 minus 0 or 1 minus 1. So a C directly translates to L, right? Now I have a particular L for every possible cut S bar, S prime, for all possible 2 to the n S's, right? And now if I want to take any particular linear combination of these S's, all I can do is just stack the L together with a particular mu prime, whatever, you know. All I need to do is take an S, mark one side of them as 0, mark the other side as 1, and just stack these vectors together. That's it. So every possible combination of these can be a vector of length, you know, vector of length, whatever. We don't really even care. Every possible combination of S is just every S is just one dimension L, and a linear combination of S is just L stacked on, like one dimensional L stacked on top of each other. So C is a subset of L. Isn't that crazy? All you need to do is think in terms of stacking, like stack. That's it. Isn't that crazy? That's awesome, right? Now, L is a subset of C. Okay, let's do that again. I assure you there's going to be a stacking of some kind. First argument is it suffices to look in 1D. Why? Because if it was a multiple dimensions, again, multiple dimensions of L are just one after the other stacked on top of each other, right? So all I need to do is convince you that 1D case holds, and then every other coordinate is just 1D repeated and stacked on itself. All of these stacking arguments, you know, the reason they hold is because we are only focused on L1. In L2 metric, we have to square this and add to the square of this and add to the square of this and add to the square of this and take a square root of the entire thing. But in L1, it's pretty easy. Take the difference of this, add to the difference of this. No other function needed. So we can analyze every particular dimension on its own. So let's only look at, let's say, 1D case, right? So here are my points. Here how is my L1 maps my endpoints. There is x1, there is x2, and then there is x sum n. there is xi, and there is some xj, whatever. Now, xi minus xj, the modulus of this, I can write it as xi minus xi plus 1 plus xi plus 1 minus xi plus 2. Basically just, splitting it into different intervals between I and j, right? And so on up till xj minus 1 minus xj. Right? And this is going to be so neat because we have seen this in the previous lecture. We have seen this entire argument in the previous lecture. So xi is here, xj is here. Forgive my notations, I'm going from superscripts to subscripts and everything in between. So to measure xi and xj, I split it into all of its sub-intervals. Okay. And now I want to turn it into a cut sort of a fashion because I want to prove that L is a subset of cut metrics, right? So the natural choice from the last particular lecture is we'll look at, let's say, level cuts, all of these level cuts. So, and I define a cut SK as containing all the left K's, so basically 1 or 1, 2 or 1, 2, 3. So this is S1, this is S2, this is S3, and SK is defined as 1, 2 up till K. Now, what I am claiming is xi minus xj is equals to the sum over all sk's dsk ij and xk minus xk plus 1 here. Is this right? No, actually this one is instead of summing over all sk, it should go from k equals to I to k equals to j minus 1. Essentially what we are saying is this xi minus xj would only be taken into account on metrics which separate these two, right? So when I'm on a metric which is this one, let's say I'm on k equals to no, this should go to n minus 1 then. Yes, yeah. It should go from all, right. Yeah, now it makes sense. Yeah, I was wrong. So let's start with here. This metric, this cut metric puts xi and xj on the same side. So dsij will be 0 in this metric. In the second metric, it puts them on the same side. It's 0 again. In this particular metric, xi and xj are put on the opposite side. So now I want to include this. So basically what I'm doing is I'm trying to increase my level sets. I'm trying to take this cut from here all the way to here. And I want to include every time I am in such a cut that xi is on the left and xj is on the right, I want to include the distance that this cut, like the L1 distance that this has moved. So when I'm here, xi and xj are on the same side, so I shouldn't count anything. As soon as I cross xi, xi is on the left, xj is on the right. So I want to include the distance, I want to include this distance that I have traveled, so which will be xi minus xi plus 1. When I'm here, I want to include this distance, which will be xi plus 1, blah. And I move, and there will be a point where I will be here, and then I will, because again xi and xj are on the opposite sides, it's again this telescoping series again. Xj minus 1 and xj, I will include this distance. As soon as I move here, xi and xj are on the same side, so this becomes 0 again, and all particular interval numbers ahead of it will add up to 0 anyways. So all I did was moved this matrix. So what I'm trying to say now is xi minus xj in this L1 is a weighted combination of cut matrix, and this weight is precisely the interval length. And we did the same thing before in the Cheeger's analysis. Yeah, I'm not doing a good job at explaining, but the idea is that when we move this cut metric, when we move this metric to, when we move this cut to here and here and here and start including more and more vertices on this side, I start pulling vertices from here to here. As soon as I pulled xi here, from the right hand side to the left hand side, I want to keep including every distance I move until I pull xj, and after that everything else is irrelevant. So dskij, so when ij on these opposite sides, it will render 1, and xk minus xk plus 1, which is the length of the interval that we have traveled. So the point being, an L1 metric is a linear combination of C's. So L is a subset of C's, because now when I take a linear combination of L's, let's say of any stack combination of L, all I need to do is take the mu times that of particular, like, right? If I take a mu times some L1 metric plus a mu times another L1 metric, all I need to do is take a mu times of this big number, like the big summation, plus a mu times of another big summation, like, which will be again defined by how it arranges its points. So it's a sum of a sum. It's a big subset. Like we are doing more work when we go from L to C, but again, it doesn't matter because C has every possible linear combination of such possible cases. So L and C, so that's a remarkable thing if you think about it. An L1 metric is precisely cut metric. Like, cut metrics and L1 metrics are the same, are exactly the same. That's the main idea. So now is the, going back, phi tilde of G is minimum over S, E S bar, which is ds ij, sum over edges divided by sum over vertices. This is VV, this is not W, VV. ds ij, sum over all pairs basically. Let me write P from henceforth, right? Edges and pairs. Please keep that in mind. Let P not mean anything else for you. Right? Yes. And I'm taking a minimum over all possible S's. So now this ratio is a little bit, off, because we worked so hard to combine mu's of S's, like mu's of D of S's. We would like to have some linear combination here. So here's where this inequality helps. A1 plus A2 plus A3 blah 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 divided by B1 plus B2 plus B3 is greater than the minimum of AI divided by BI. Right? And why is this the case? Well, if this minimum was achieved by, let's say, some number m, then every AI is greater than m times BI. So I can put that every AI is greater than m times BI, and every AI is greater than m times BI. I can pull the m outside and all of those BI's will cancel. So this will always be greater than this particular number. Right? This is a fact. Like, you can convince yourself. It took me a while to convince. It took me some time to convince it to myself too. But this holds, and it's nice because now it lets us convert this minimizing over all i's. This will be. So let me try to paint a picture. Let me try to draw some correlations. If I make this as all combination, all S combinations, then right hand side is just this, what I'm talking about. So let me do that actually. Instead of writing the minimizing over ds ij, edges and pairs, let me write it as a sum over all s's now. Sum over all s's. All I want to do is do this. Sum over all s's, divide by sum over all s's, sum over all edges, sum over all pairs, dsij, dsij. And again, I can multiply by, I can again, take a weighted sum. It wouldn't matter, because when I take the weighted sum, I multiply the numerator and denominator of the same like of a1 with a mu1, let's say. And when I take the division here, it cancels out. So I could do that. Wouldn't matter much. So now I see that this number is always going to be greater than this number, and we want to minimize this. Or basically, now what I want to do is I want to minimize this quantity and approach it from the top. Like I approach it from the top, and it will be eventually be equal to whatever this minimizer was. Right? So let me, clean it up a bit. Let me take the mu s's inside, and let me take the edges outside. Let me use a Fubini's theorem. It becomes summation over edges, summation over all possible cut metrics, divided by summation over pairs and combination of all cut metrics, essentially. All I did was take the sum inside, right? And the mu is inside too. Like I can multiply that. It doesn't matter. Right? Now, another thing to note is that this number is essentially one element like this, because cuts and L1 metrics are the same. This is equal to an L1 metric. I want to minimize this over s's, right? Find the minimum over all mu s actually. But this is pretty simple, because this is now a minimizing over D is an L1 metric. Summation Dij, where this is edges, and summation Dij, where this is all pairs. This is what we have been doing for the entire, half an hour. Like we wanted to show that a combination of cut metrics is exactly equal to a L1 metric. So the optimization now, I can set, let's say I do this. Find the minimizer over all edges, Dij, subject to that the sum over all pairs, Dij, is equal to 1. Basically, I set the denominator to be equal to 1. I force it to be 1. And then I have to minimize this, and D is a L1 metric. D is an L1 metric. So the next thing is LP relax. I throw a LP relaxation at it. The LP relaxation then is minimize sum of edges Dij subject to sum of pairs Dij is 1, and D is any metric, not constrained to L1. It's any metric whatsoever. Doesn't matter to me. Now, how do I enforce this constraint? All I need to do is write the NC3 triangle inequalities. I can write Dik less than Dij plus Djk for all triples as a separate inequality, and therefore I have this is a metric. I have enforced it to be a metric. I have no care whatsoever if it's an L1 metric. It just needs to be a metric which satisfies this, which satisfies this and a bunch of triangle inequalities. And I can solve it now. Let's say I solve it. Let's say I find an LP relaxation and I get a number. And I get a number for every D. I get an endpoint metric that is X and has a function D, which takes every 2 points and maps it a number. Like every Ik will be mapped to a number. However, this is not in an L1 metric. So the theorem now, the main theorem, which we will go to in the next lecture, theorem of Bourgain. is that I can embed, like I can take this metric D, which is any arbitrary metric, it doesn't have to be L1, L2, L infinity, whatever, and I can embed it into an L1 metric without losing much, with incurring some distortion. Like you cannot exactly preserve all distances, otherwise that would be like, what the hell. You cannot exactly preserve every distance, but you won't lose too much, you won't lose too much. So the theorem of Bourgain is, let me read from my notes. Oh my god. The theorem of Bourgain is that let me use another sheet. That given an endpoint metric x and d, there exists a function phi which maps these x to an L1 space of, let's say, m dimension, such that phi I minus phi j, the L1 norm, is less than f of n times dij and greater than dij. So basically what they're saying is that I said it opposite, but this also is the same thing. You will always stretch every particular distance, but you will not stretch it too much. So f of n is log n, like up to some constants theta, let's say. So the point he's trying to make is that obviously you will incur some distortion when you embed any arbitrary metric into a L1 metric. You will incur some distortion, but that distortion will not be too bad though. It will only be a logarithmic, and log, we don't have any respect for log function because it's just a flat line, almost not a flat line. But log n is 100, let's say, for all intents and purposes. It cannot be more than 100, So that's a very remarkable, result if you think about it. But how does it relate to our phi tilde of g that we wanted to, So the first thing is that the LP value, because it's a minimum over all metrics, and I relax it. What is phi tilde g? Phi tilde g was edges s bar divided by s bar, which was the sum of ds divided by the sum of ds over all pairs over all edges. And this is what we tried to LP, right? This is what we were LP. This is what we did the LP on. And because it's a minimization, the LP will always be less than phi of g, phi tilde. But how much is it? Well, greater than. How much is it losing? Well, because we saw that Bourgain's theorem hold, we can now say that this is always going to be 1 over log n. But let's prove this. Let's prove that 1 over log n factor is true. So let's say our LP, yeah. Oh, I'm going through slides, like I'm going through sheets of paper today. Let's say our LP returned a D star, D star, and I did not embed it yet. So the LP of G is D star ij sum over edges divided by D star sum over pairs ij, right? And now I embed it into a phi. So let that phi be the L1 dimension, L1 embedding. Let the phi be that L1 embedding. So what we are claiming is from the Bourgain's theorem that phi I minus phi j is less than log n d star ij and greater than d star ij, right? So I want to prove that LP is greater than something. That means I want to reduce, so I want to put something less than here. So D star is always less than, oh, so D star is always greater than, D star is always greater than 1 over log n phi, right? I will put that here. And then I will put that D star is always less than phi, and I will put that here. So right, so this becomes forgive me, this becomes that LP of G is always greater than 1 over log n psi I minus psi j divided by psi I minus psi j. Like I put the D star is greater than something on the numerator and D star is less than something on the denominator. So division of that will always be greater than this particular quantity. So this is LP is greater than 1 over log n, 1 over log n psi I minus psi j divided by psi I minus psi j, or sum over pairs, sum over edges. That's the LP. So what we wanted to show now, what we were trying to show that LP is greater than, we're trying to show that LP is greater than this thing. So what we need to show that this quantity is greater than phi tilde of G somehow, just this quantity. And if we are able to prove, if we are able to reason about this, then we are done. Well, this is just, this is an L1 embedding, right? So this is just some D L1 embedding, but it is the same thing, ds ij over ds ij, edges and pairs. Just that this is an, if I look at an L1 embedding as just a cut metric, this is the same. So this is always going to be greater than the minimum of all such things, right? I don't really know what the phi tilde is, but I know that this will be greater than phi tilde. So LP of G is greater than 1 over log n of, phi tilde. Does that make sense? Yes, because this is a minimum over all L1 metrics. And this is just one particular L1 metric. So it makes sense, in fact. So we actually have found a, log n approximation to the phi tilde thing, which is again something which is very close to the phi, like the actual sparsity. Right? Yeah, I'm confused today. This is not my strongest, but what we tried to do was, you want to recap today? Like, you want to recap a little bit right now? Let's do that. Let's recap. We approached all of this with the intuition that cut metrics and L1 metrics are the same. So that is okay. I understand that. Phi tilde G is a minimum over this, minimum of this, which is the minimum of the division, which is actually the minimum of the combination of everything. And a combination of everything is just another cut metric, which is just another L1 metric. So I find the minimum over L1 metrics. I cannot do that, let's say. I don't really know how to do the L1 thing. So I relax it and make it any metric. And I can do any metric because any metric just needs to satisfy this particular, all of these n choose 3 or n choose 3 or n cube inequalities. Right? So I do the relaxation. I find such particular values, and now I need to embed it back into L1 because I need to go back and find a cut, because All of this was to find some sort of a sparse cut. So I need to embed it. And now the Bourgain says that you can embed any D metric into a L1 metric such that you only lose a factor of Fn, or let's say you only stretch or distort yourself to a factor of log n. So my phi tilde G was the division of this. This was what we are trying to LP approximate. And LP is a minimization, so it's always less than phi tilde G. I want to say that LP is greater than some phi, some function, something. And what we have is that, let's say the D star be the metric, like the arbitrary metric returned to us by the LP, and phi be the embedding. Bourgain says that you can only stretch up to a factor of log of n. So D star is greater than, D star here is greater than 1 over log n times the psi. So I put that here. I get this is greater than 1 over log n of psi divided by D star is less than psi itself. So I put that in the denominator. I get the double whammy, and I get that this LP is greater than 1 over log n, the psi divergence on edges divided by the psi on the pairs. But this psi is an L1 metric, and this has to be always greater than the minimum over all L1 metrics, which is indeed phi tilde G. So LP is greater than phi, LP is greater than 1 over log n phi tilde G. That's cool. That's cool. So let's say someone asks me, let's do this for the completion. Give me the algo. That's it. I don't care about anything else. Just give me the algo. All right. The algo is this: LP relax Dij over edges such that Dij over pairs is equal to 1. This is that fraction, and D is a metric, so there are n cube inequalities here. I get this D, right? Let's say D star. Embed D star. This was step 1. Step 2, embed D star to psi, right? From calling Bourgain's black box. We don't really know how Bourgain did it. We'll do it. We'll look at it in the next week. But using Bourgain's black box, let's embed D star into psi. And now psi is an L1 embedding with, I don't know how many ever dimension. I want to express this as a cut metric, as a linear combination. Linear combination of cuts. How will we do that? Let's say we do that separately for every possible dimension. We did that, and within each dimension we have, let's say, arranged it in this particular manner, and we can look at all of the cuts which are generated by the level sets, and the mu s will be these particular intervals. So what we are going to do now is, in every dimension there will be n cuts, and there could be how many ever dimensions there are. So the we'll see it next lecture that the number of dimensions are also polynomial in n. So this entire thing is tractable. It's polynomial. For every dimension, you look at the level sets and you correspondingly take the cuts of those level sets with their particular weightings. So you have a set of cuts, and then you can do what you can do then is find the best S star, which minimizes this particular quantity. You have a collection of all of these cuts, one for each dimension, and amongst every dimension you have all of these, cuts with their weightings. You need to do S star, which is the one which minimizes this quantity, S bar divided by S this. You can just calculate this for every possible cut. There are only polynomial many cuts, so you can do this. Take the best cut among this. That's the algorithm. So whoa, okay. So the main idea was that you can embed main math. Let's even forget the computer science. Let's forget the algorithm. The main math here was that take any metric, man. Take any endpoint metric, and you can. It's essentially the same as an L1 metric, which is boggling to think about. Like take any endpoint metric, and you can embed it with some distortion, of course, into an L1 metric, man, which is crazy. It's bonkers. So we started with the problem definition. We started with graph partition. I mean, I forgot about graph partition altogether. Graph partition is separating the graph into two such that they are balanced and the number of edges are few. That is a clustering problem essentially. So this is crazy because if you have a graph, you can find connected like clusters amongst that graph. Not appropriately, not accurately, but you can do that. You can do that through the Sparsest Cut algorithm. What you can do is, keep doing the Sparsest Cut algorithm again and again and again until you are satisfied until your satisfaction is met. So Sparsest Cuts leads to balanced graph partitioning. So now let's focus on the sparsity, where the sparsity is defined in this tilde manner because it's symmetric and it's a nice definition of sparsity. We define the cut metric where every point on the same side is at distance 0 and every point on every pair on the opposite side is at distance 1. This is indeed a metric. And now the sparsity in the new definition is just the sum over edges of the cut matrix for sum over edges and divided by the sum of all pairs. And now we have the fact that a linear combination of all of these cut metrics are indeed in a cut metric, and this is exactly equal to, so two things here, like the cut matrix is exactly equal to an L1 metric, and every endpoint metric is a L1 metric up to a factor of log n. So basically every endpoint metric is a cut metric is a combination of cut metrics, which is crazy. Like think about it. So Cn is a linear combination of all cut metrics, and L1 is every possible L1 space dimension, whatever, and these two are exactly the same, like, which is a crazy thing to think about. And we did that by showing that L's are also closed under a positive combination. What we can do, all we need to do is just stack the two vectors on top of each other, and you have created another space which preserves the distances on the two sub whatever, like these two are the same. Not the sub, I wouldn't say sub, but the two constituent metrics. And to go from C to L, all you need to do is map one side of C to L and map the other side to 1. Map one side to 0 and map the other side to 1. And a linear combination of them can be just expressed by stacking them on top of each other with appropriate weights. And L is the same because for L you need to rearrange them in a line, let's say, and take level sets. And while you take level sets, also weight those level sets appropriately when those weights are exactly the intervals on this level sets. Again, crazy, that's crazy. So now the minimizer of the sparsity is using this inequality. All you need to do is take all combinations of S and it will always be greater than the minimum. So if I try to minimize this fraction, I will end up to that I'll reach there from the top down. And this fraction is just a linear combination of all cuts with appropriate weights. I don't really care, which is exactly the same as an L1 metric because that's how we worked with. That's what we worked with. Like every possible linear combination is an L1 metric. So we did that. And so this is the optimization. Find the minimizer over Dij such that over edges such that the sum of two pairs is 1 and it's an L1 metric. But we don't really know how to do this optimization, so we relax it to make it equal to any metric. And to ensure that, all we need to do is have some n cube triangle inequalities and we can satisfy them independently, and we will be able to get to a D star, let's say, metric. And from there, what we need to do is embed it into again an L1 metric, because we need to go back and get that phi tilde G. We embed it back into an L1 metric using Bourgain's black box, Bourgain's theorem, that when you embed it into a psi space, you can only stretch by a factor of f of n. Like, you cannot be too crazy with the distortion. You will incur some distortion, that's natural, but not too much. And from there, we have found a 1 over log n approximation of the sparsity. And again, so all of this is just saying that now you have a 1 over log n approximation of the sparsity, and therefore you have a 1 over log n, 1 over alpha log n, whatever fraction you want, of the balanced graph partitioning problem. So this is a very nice toolbox, nice tools. Think about the sparsest cut and the Bourgain's embedding, and we will get into Bourgain's theory, the Bourgain's math, in the next video.